Hi, good afternoon, everyone. My name is Rita. Standing beside me is Abhishek and Arvin. We're from Microsoft. We would like to talk about today's AI world and how we can enhance the hyperscale network observability and operational excellence. As we all know, since last year, after ChatGPT was launched, it had gone viral. The use of AI has grown exponentially around the world. So it's used commercially and also used by many people down to high schoolers. And many businesses also plan to invest in AI currently, right? So these are a lot of the demands of AI means that we also need to raise the bar for how we design the data center networks. So today we'll mostly concentrate on networking and because of the influence of the AI. So some of the typical workloads in AI, of course, is the machine learning and deep learning. Deep learning is a type of machine learning using neural networks to analyze very complex relationships and data relationship in the data. And then there are AI-enabled applications. For example, for example, there are these different types of workloads are, for example, recommender systems. When we listen to music from YouTube, these are type of recommender system which recommends the type of music we like. And companies like, for these systems, it's best deployed in the cloud because we already have all the storage and the APIs and the tools for deploying the AI models. And then the ChatGPT is a type of natural language models, which needs very high response and fast response. Computer vision is basically a type of model which analyze images to derive meaningful information. So these are the typical examples of the AI workloads in the cloud. And therefore, because of these high demands, we will need thousands of CPUs in purposely built servers to deploy in a data center. And these GPUs or servers actually have very high speed NICs compared to the traditional servers. There are 200 gig NICs, 400 gig NICs, etc. Right? So basically, the demand for the speed in the network has just gone up a lot because of AI, and the requirements actually is not really just at the GPU servers level, but it's actually all, needed in all the tiers of the switches in the data center, from top of rack switches to leaf switches or spine switches in the data center. When we have higher speed network, then it can help to reduce the training time that is needed in AI, right? And because typically when we train data, sometimes it might need days to finish a complete training. So and then if you any job failed and if you wanted to retry, that's an increase of the cost. So you don't want that to happen. And to minimize the network failure, we need to have very efficient network management, monitoring, and visibility. And then of course, the other type of scenarios is the AI applications. So those we would like the responses to come fast. And so in the networking, that means that we need to have very low latency. Customers deploying AI in the cloud also would like to have privacy and security. So the network needs to provide network isolations or encryption capability. So let's go slightly deeper on how we can design the data center to support AI workloads. As I mentioned, there's two major scenarios, right? There's the model training, and then there's the inference scenarios. So when we train a model, the data is actually long-lasting, because it can take days, right? And then the data requirement is actually high. It would need some more utilization or bandwidth for the link. We call these types of data flows elephant flows. Yeah. And then the other scenario is inference. But so then, in the contrary, this type of data is actually short-lived and bursty. So we want to have our equipment, our networking equipment, able to handle these kind of contradictory characteristics of the traffic. And then when we often, of course, we also would need to, sometimes we also need to share data across different geographical sites. And then after we finish training our data, right, then we also need to transport the data from the GPU focus clusters to storage clusters. So as I mentioned, we would like these data transfer to be lossless and very reliable. So RDMA is actually a technology enabling memory access across servers without involving the CPU cores. And with this, then it actually enables high throughput and low latency for the GPU clusters to have data read-write across different sites. And then to actually transport RDMA data across clusters, we use RDMA over Ethernet, Rocky V2, to transport AI data between GPU-centric compute clusters and storage clusters. Finally, the link utilizations can be high, and also there could be buffer builds up in the switches. So we definitely need to have congestion management strategy to manage the network congestion scenario. DCQCN is something that we could use. It uses a combination of PFC and ECN for end-to-end connection management. There are also switch ASICs out there with credit scheduler and VOQs. So these systems are very good in further minimizing the congestion in the network because only if there are bandwidth available in a port, then packets are sent out of ports. So these are some of the essential technology or strategy we need in order to design a data center network for AI workloads. So as we could see, we want our networking systems to be very well designed to prepare for the AI demands in the data center. Sonic is a Linux-based network operating system running in networking switch systems from hardware vendors. In Microsoft, Sonic is widely used in many switches of the data center. For T2 chassis, which is on the spine layer, but that's at the edge of the data center, it's also Sonic is supported in a disaggregated fashion. So a chassis system it's a lot more complicated than a pizza box switch. It has a supervisor card, like a control card, a number of fabric cards, a number of line cards with front panel ports. And line cards can have CPU and can have a number of switch ASICs. And then the switch ASICs typically are connected in a cross fashion. So with this hardware design, we can apply Sonic in each of the modules of the chassis system. So we use a multi-ASIC Sonic software design on each of the modules of the chassis. In other words, we are using a disaggregated approach to support Sonic in a traditional chassis system. I will now pass on to Arvind to have more deep dives for this approach.
Yeah, so as Rita mentioned, a chassis typically has a lot of components. But from most of the network management services point of view, it is treated as a black box. So it's modeled as any pizza box with the links connecting to its peers in the network. So with the disaggregated design, we are exposing the internals of the chassis to all the monitoring and configuration services. So for that, all the internals of the chassis are exposed. So we expose the internal links connecting between the line cards, the control plane information required for the line cards to communicate with each other, the fabric information, all the fabric ASICs and so on within the chassis get exposed to various services for various use cases, which we'll see in the subsequent slides. Okay, so one of the design principles of the disaggregated chassis is we use standard BGP to synchronize information, specifically routes between the line cards. So in this example here, the chassis has 3 line cards, and we run IBGP between the line cards to exchange routing information. So as as Rita was saying, like, since we treat each component of a chassis as a separate network entity, so then we could use standard networking tools, which we use on other parts of the data center to also manage the components of the chassis. An example would be we could isolate a specific line card just by applying BGP route maps, rather than using any proprietary or vendor specific way of isolating a device. Rita? Yeah. So with this new modeling, so how does the whole configuration work? So again, so each of these component in a chassis could be treated as a network device. So just like we generate configuration for a Tor or a leaf router, we could generate configuration for a line card, which would be self-contained so that the line card could operate on its own. Within the line card itself, there could be multiple ASICs. So we have a config DB in Sonic, which is a repository of the configuration for that specific ASICs. So this will have all the necessary information for the ASIC and the ports in this ASIC to operate independently. Next slide. So Rita was mentioning about elephant flows and different types of flows in AI and ML. So load balancing is a very interesting topic in an AI network. So typically we could design a disaggregated chassis by disaggregated system and use either spraying, where the packet gets sprayed to all the receivers for load balancing, or we could use any of the adaptive routings available to take into consideration the link utilization, the queue depth, and so on, so that we could better load balance the traffic within the chassis itself. So as I mentioned in the previous slide, so with this modeling, we have the capability to configure a specific ASIC. So based on the deployment, what kind of clusters are configured, then we could fine tune a specific ASIC based on the traffic pattern that ASIC is, or the ports connecting in that ASIC is expected to receive. So if you have traffic coming from, let's say, compute to RDMA, we could have a different set of buffer profiles or QoS profiles, whereas if you have traffic within a compute cluster itself. So this gives flexibility for operator to pick and choose different load balancing schemes based on the deployment. Yeah, then Abhishek will cover other use cases.
Okay, so next few slides will go how this disaggregated chassis and the modeling help us with the visibility and the availability of a disaggregated Sonic chassis. So as we see in this picture, once we disaggregated the chassis from the management controller perspective, all the supervisor and line card modules act like a separate IP endpoints. And we are able to run all the management services like SNMP, telemetry, syslog on each module separately. And then we are able to collect all the data from different ASIC and can export to the controller. So basically, from a controller perspective, they are like any other separate IP endpoints and to get the data. So let's take an example of how this helps with a control plane monitoring. So since Sonic is running on each instance of supervisor and line card, so all the control plane health monitoring, like any process crash, CPU memory high usage, any failure, this can be caught at each module level, and then this data basically is available and can be exported to the controller. And once this data is exported, any mitigation action like process restart, reboot, all this can be done independently. So we don't have to reboot the whole chassis, like whichever module is facing the issue, we can reboot that. So next I will talk about a little bit of high availability that we have in the disaggregated chassis. So if you see in this picture, as Arvind mentioned, we use IBGP for connecting across line cards. But the problem with iBGP is like if there's any remote fault or any line card unplanned reboot, the detection time can be high. So to solve that problem, we are using BFD. So BFD being a hardware offloaded feature, we get better convergence. We detect the remote fault quicker and take an action. Plus, since with the modeling of each internal ASIC and line card separately, we have the visibility of the internal links between line card and the fabric ASIC. And thus, we can detect any CRC errors, uncorrectable errors that are happening on internal links. And we can take action to mitigate those links if they are crossing some threshold. Similarly, if the issue is like a lot of links are flapping or a lot of links are seeing errors, we can always isolate a given ASIC also, since Sonic is controlling each ASIC. So yeah, this slide talk about little bit of data plane visibility that we have. We can, since Sonic is running on each line card separately, we can do a probe of line card, like to see the liveliness of each line card. So we can probe the loopback IP of a line card from a controller or vantage point, and it can come to the line card, and we can see the liveliness of that line card. Similarly, we can see the liveliness of each ASIC also. So since we have running iBGP across ASIC, we have an IP endpoint for each ASIC. So we can probe a packet, send a probe packet for a given ASIC, and it can go via fabric and check the liveliness of another ASIC and get returned back to the vantage point. Similarly, I think one of the pain points for debugging in chassis is the drop packets. So with the disaggregated chassis, we can do all these drop packet captures, or copy or mirror them to CPU on each line card independently. So if we know the port that is dropping the traffic, we can pin to that particular ASIC and do all this drop capability counters and copy them to the CPU. Similarly, as I think we have heard in multiple presentations, like one of the requirements for AI traffic is a lossless traffic. So running a disaggregated chassis helps us with giving counters and the visibility of all the internal links. So we have the queue counters available for all the internal links for different queues. So these are some of the use cases that disaggregated chassis brings with for control plane data plane monitoring. I think I'll have Rita do.
Yeah. So because of AI, right, we are seeing a lot of innovation opportunities to improve the efficiency and capacity for all these AI workloads. So I encourage everyone to continue to collaborate in the open source community. And for networking, Sonic is a very popular open source network OS. And we need to continue to innovate in Sonic. And actually, the ecosystem has both software and hardware. So please continue to collaborate and contribute to these areas for this era of AI. So we do have a lot, quite a few big networking players who are contributing to Sonic chassis. So these are the major vendors in the industry. I again acknowledge and appreciate their contributions.
Thank you.
Thank you.
Thank you.